This paper introduces the concept of de Bruijn arrays codes, a two-dimensional generalization of perfect factors in the de Bruijn graph. A de Bruijn array is defined as a set of R times S binary doubly periodic arrays, where each binary n times m matrix appears exactly once as a window in one of the arrays. This concept generalizes unidimensional sequences with a window property to two-dimensional arrays with a window property. The de Bruijn graph G sigma n is a directed graph, where the set of vertices Vn has sigma n vertices represented by the set of sigma n words of length n over an alphabet of size sigma. A span n de Bruijn sequence is a cyclic sequence of length sigma n in which each n-tuple is contained in exactly one window of n consecutive digits. This paper focuses on binary arrays, but notes that some results can be generalized to any alphabet size. The concept of de Bruijn arrays is a natural generalization of de Bruijn sequences, which have found various applications in pattern recognition, camera localization, and surface measurements. Previous work on perfect maps, a synonymous term for de Bruijn arrays, includes constructions by Reed and Stewart, Gordon, Clapham, Ma, Fan, Ma, and Su, and Patterson. This paper aims to provide necessary conditions for the existence of de Bruijn arrays, as well as direct and recursive constructions for such arrays. A framework for a theory of two-dimensional feedback shift registers is also suggested, analogous to unidimensional feedback shift registers. De Bruijn arrays have been extensively studied in coding theory, image processing, and cryptography, but this paper extends these results to de Bruijn arrays codes, defined as sets of doubly periodic arrays. Specifically, a de Bruijn arrays code is a set of R times S arrays, where each non-zero n times m matrix appears exactly once as a window in one of the arrays, denoted as an R, S, N, M, DBAC. The necessary conditions for the existence of an R, S, N, M, DBAC are presented in lemma 1, which states that R greater than N or R equals N equals 1, S greater than M or S equals M equals 1, and increment equals Rs equals 2 nanometers. These conditions imply that R, S, and increment are powers of 2, denoted as 2k and 2t. The paper is organized into sections, with section 2 presenting the basic definitions and theory for the arrays. This section covers shift registers, the shift operator E, the dimorphism, perfect factors, and graph representations. The shift operator E is essential in defining the linear complexity of sequences used in the constructions of two-dimensional arrays. The dimorphism defines a homomorphism between de Bruijn graphs of different orders and is used in the recursive constructions of de Bruijn arrays. Perfect factors are structures used in both direct and recursive constructions of de Bruijn arrays and codes. The paper presents various constructions of de Bruijn arrays codes, including direct constructions and recursive constructions. Section 3 is devoted to 5 direct constructions, while Section IV presents 5 recursive constructions. These constructions generalize existing methods for constructing de Bruijn arrays and are used to generate 2k, 2t, n, m, DBACs. The rest of the paper explores techniques for generating de Bruijn arrays codes, including joining codewords of an 2k, 2t, n, m, DBAC with shorter arrays. The constructions presented in this paper extend existing methods for constructing de Bruijn arrays and provide new techniques for generating de Bruijn arrays codes. Doubly periodic arrays, specifically de Bruijn arrays and pseudorandom arrays, are the focus of this research. A de Bruijn array is a binary R times S array where each non-zero n times m matrix appears exactly once as a window. In contrast, a pseudorandom array is an R times S array where each non-zero n times m matrix is contained exactly once as a window, with a shift in DAD property. The concept of shortened perfect maps, or shortened de Bruijn arrays, is also introduced, where R times S binary arrays with Rs equals 2 nanometers 1 have each non-zero n times m matrix appearing exactly once as a window. To construct de Bruijn arrays codes, the paper explores preliminary concepts, including feedback shift registers and their sequences. A feedback shift register of order n has 2 n states, represented by binary words of length n, consisting of n cells connected to a logic element that computes a Boolean feedback function. The register operates with an initial state, transferring values between cells according to the feedback function at periodic intervals controlled by a master clock. The feedback function can be represented by a truth table, with 2n possible distinct values for the states of the register. These concepts will be generalized to two-dimensional setups and used in the construction of de Bruijn arrays codes in subsequent sections, enabling the development of novel coding schemes and applications. Feedback shift registers, FSRs, are considered, where each FSRN has 2n distinct states, each with a value of either 0 or 1, resulting in 2n different FSRNs. However, not all of these functions are of interest. Each FSRN has a state diagram, a graph with 2n vertices, representing the states of the FSRN, and exactly 2n edges. A non-singular FSRN has a feedback function whose state diagram contains only cycles. A factor in a graph is a set of vertex disjoint cycles that contain all the vertices in the graph, and a factor in G_n is associated with a state diagram of a non-singular FSRN. Lemma 2 verifies non-singular FSRNs, stating that an FSRN is non-singular if and only if for each x_i element of 0, 1, 2 is less than or equal to I is less than or equal to n, f, 0, x_2, x_n, does not equal f, 1, x_2, x_n. Corollary 1 further states that an FSRN is non-singular if and only if for each x_i element of 0, 1, 2 is less than or equal to I is less than or equal to n, f, x_1, x_2, x_n, equals x_1 plus g, x_2, x_n, where g, x_2, x_n, is any Boolean function with n1 variables. A non-singular linear feedback shift register of order n, or LFSRN, is an FSRN with a linear feedback function, where x_n plus 1 equals f, x_1, x_2, x_n, equals x_1 plus underscore I equals 2, nc_i x_i, c_i element of f_2. 1 is less than or equal to I is less than or equal to n. There are 2n1 non-singular feedback shift registers of order n, but only 2n1 non-singular LFSRNs. 4 feedback functions are defined. The PCRN, pure cycling register of order n, with linear feedback function f, x_1, x_2, x_n, equals x_1, the CCRN, complemented cycling register of order n, with nonlinear feedback function f, x_1, x_2, x_n, equals x_1 plus 1, the PSRN, pure summing register of order n, with linear feedback function f, x_1, x_2, x_n, equals underscore I equals 1, nx_i, and the CSRN, complemented summing register of order n, with nonlinear feedback function f, x_1, x_2, x_n, equals underscore I equals 1, nx_i plus 1. The length of the cycles in the state diagrams of these shift registers, which corresponds to the period of the associated sequence, is of special interest. The period pi, s, of the cyclic sequence s equals s_0 s_1, s_n1, is the least positive integer pi such that s_i equals s_pi plus I, for each 0 is less than or equal to I is less than or equal to n1, where indices are taken modulo n, when the sequence is cyclic. A cyclic sequence S of length n is defined as a sequence where, for any integer pi dividing n, c equals s pi plus I for 0 is less than or equal to I is less than or equal to n1 is a period of S, with the period being the smallest such integer. Two cyclic sequences are considered equivalent if one is a cyclic shift of the other. Previous works, including comprehensive books on shift register sequences and the de Bruijn graph, have studied the length and period of sequences generated from shift registers. A cycle in the state diagram of a linear shift register can be represented by a sequence whose length equals the cycle length, generated from the first bits of the vertices in the cycle, in their order. The concept of companion vertices is introduced, where the companion of a vertex x is the vertex x, obtained by flipping the last bit of x. The complement of a state x is defined as the state obtained by flipping all bits of x. A cycle S is self-dual if its complement, denoted as S, is equivalent to S. A sequence S is self-dual if and only if it has the form S equals XX, where X is a sequence and X is its complement. The mergeosplit method is introduced, which involves merging two cycles C1 and C2 into one cycle C by interchanging the predecessors of a state X on C1 and its companion X on C2. This operation can either merge two cycles into one or split one cycle into two, as depicted in Figure 2. The shift operator E is a fundamental component in the representation of feedback shift registers' properties. It shifts the entire sequence to the left, where for a sequence S of length k, SC equals C plus 1, and if the sequence is cyclic, SC1 equals S0. When applied to a cyclic sequence, E, S0 S1, SK1 equals S1, SK1 0, and when applied to an acyclic sequence, E, S0 S1, SK1 equals S1, SK1. Any periodic sequence satisfies a linear recursion C plus M equals A1C plus M1 plus M1C plus 1 plus AMZ, where a j element of 0, 1, and all computations are done modulo 2. This recursion can be represented using the shift operator E as MC equals Mn array summation j equals 1 AJEMJC. If M is the smallest such integer, it implies that M does not equal 0. The polynomial f, E, equals M plus Mn array summation j equals 1 AJEMJ generates the sequence S if f, E, C equals 0 for each I is greater than or equal to 0. The linear complexity C, S, of a sequence S is defined as the least M for which the linear recursion holds, and it is clear that C, S, is less than or equal to k for any sequence with period k. The sequences of interest have lengths that are powers of 2 and are generated by the polynomial E plus 1, k, where E plus 1, ks equals 0. Two properties of these sequences are characterized by lemmas 3 and 4. Lemma 3 states that a sequence S of length 2n has linear complexity C if and only if E plus 1, circa 1s equals 2n. Lemma 4 states that there are two n lone 1 sequences generated by the polynomial E plus 1, n plus 1 that are not generated by the polynomial E plus 1, n, all of which have period 2 lone plus 1 and linear complexity n plus 1. The weight of a word or cyclic sequence is defined as the number of non-zero entries, and some additional properties of sequences are characterized by lemmas 5 and 6. Lemma 5 states that for n is greater than or equal to 1, a sequence S of length 2n has linear complexity C greater than 0 if and only if the linear complexity of the sequence, E plus 1, S is C1. Lemma 6 states that for n is greater than or equal to 1, a sequence S of length 2n has linear complexity 2n if and only if its weight is odd. Lemma 7 establishes a fundamental connection between self-dual sequences and linear complexity, demonstrating that a sequence of length 2n plus 1 has linear complexity 2n plus 1 if and only if it is self-dual. The authors then investigate the linear complexity of de Bruijn sequences, presenting Theorem 1. Which provides bounds for the linear complexity of span n de Bruijn sequences. Specifically, for n is greater than or equal to 3, the linear complexity C, S, satisfies 2n1 plus n is less than or equal to C, S, is less than or equal to 2n1, with C, S, does not equal 2n1 plus n plus 1. Moreover, the authors show that there exist span n de Bruijn sequences achieving both bounds. Conjecture 1 proposes that for any integer c within these bounds, except for 2n1 plus n plus 1, there exists a span n de Bruijn sequence with linear complexity c. The dimorphism, introduced by Lempel, is a 2-to-1 mapping from Fn2 to Fn12, where n is greater than or equal to 2. It is defined as d, x1, x2, xn, equals x1 plus x2, x2 plus x3, xn1 plus xn, equals e plus 1, x1, x2, xn. The dimorphism has an inverse, d1, which can be applied to sequences of even or odd weight, producing complementary or self-dual sequences, respectively. Lemmas 8 and 9 reveal crucial properties of the dimorphism. Lemma 8 states that for a non-zero sequence S of length 2n, C, S, equals C, ds, plus 1, highlighting the connection between the linear complexity of a sequence and its image under the dimorphism. Furthermore, lemma 9 shows that if f is a factor in Gn, then d1f is a factor in Gn plus 1. The authors also define the application of the dimorphism and its inverse multiple times, denoted as dk and dk, respectively, which can be used to generate new sequences from a given sequence S. This section of the research paper delves into the properties of the operator d and its inverse d-1, shedding light on their implications for vertex disjoint cycles in graphs. Lemmas 10 and 11 elucidate the relationships between the linear complexity of cycles in Gn and their corresponding cycles in Gn plus 1. The authors introduce the concept of perfect factors, a pivotal notion in the paper. A perfect factor PFP alpha, n, k, in GP alpha, n is a set of P alpha n minus k vertex disjoint cycles of length pk, where p is a prime and alpha is greater than or equal to 1. The authors focus on the case where p equals 2 and alpha equals 1, denoted by pf, n, k. The existence of perfect factors is characterized by theorems 2 and 3, which establish that a perfect factor pf, n, k, exists if and only if k is less than or equal to n less than 2k, and a perfect factor pf2 alpha, n, k, exists if and only if n plus 1 is less than or equal to 2k is less than or equal to 2 alpha n, respectively. The authors are particularly interested in perfect factors where the weights of all sequences are either even or odd, and where all sequences have the same linear complexity. Theorem 4 characterizes the parameters of perfect factors with even weight sequences, showing that such factors exist when k is less than or equal to n less than 2k1. And that there exists a unique perfect factor with odd weight sequences when n equals 2k1. The proof of Theorem 4 involves the use of lemmas 4, 6, 8, 10, and 11, which establish the relationships between the linear complexity of sequences, their weights, and the properties of the operator d. The authors also utilize the concept of de Bruijn sequences to construct perfect factors with even weight sequences. Perfect factors with sequences of odd weight are explored, building upon Theorem 4, which proves that all sequences in a PF, n, k, have odd weight when n equals 2k1. This technique can be applied to construct perfect factors with odd weight sequences for other parameters, although it remains an open problem whether such perfect factors exist universally. Notably, if a sequence S is in the perfect factor F, its complement S is also in F, unless F contains exactly one sequence. By lemma 7, all sequences of length 2k are self-dual if and only if they are of linear complexity 2k1 plus 1. Examples are provided for k equals 4 and k equals 5, demonstrating perfect factors with sequences of even and odd weights for various values of n. A special type of perfect factor, pf, n, n1, is of particular interest, where two sequences S and S exist, and one of them is a span n-half de Bruijn sequence. The paper then shifts focus to the graphical presentation of two-dimensional arrays, defining a graph Gn, M, V, E1, E2, comprising all two n times m binary matrices, with E1 and E2 representing vertical and horizontal connections between matrices, respectively. A set of doubly periodic matrices of size 2k times 2t is equivalent to a set of disjoint components in the graph Gn, M, V, E1, E2, where each component contains 2k plus t vertices induced by windows of size n times m in the matrices. These vertices and edges form a factor with edges from E1 and a factor with edges from E2 in the subgraph induced by the vertices of the component. Additionally, a second graph, previously defined in 8, is suitable for codes where all columns of the matrices forming the codewords are cyclic shifts of a single column. In this research paper, the authors construct a graph GF, M, which represents sequences of perfect factors. This graph is based on a perfect factor Pf, n, k, and its vertices are 2k times M matrices that are periodic only vertically. Each matrix X in the graph can be represented as a combination of cyclic shifts of cycles in F. The edges in the graph are 2k times M plus 1 matrices, also periodic only vertically, connecting two vertices. The graph has 2n mk vertices and 2n m plus 1 k edges. A Hamiltonian cycle in GF M can be represented by a vertically periodic 2k times 2n mk plus m1 matrix, where each n times m matrix is contained exactly once. If the first m1 columns of this matrix equal the last m1 columns without a cyclic shift, the Hamiltonian cycle can be represented by a doubly periodic matrix, forming a 2k, 2n mk, n, m, dBAC with one code word. This condition is satisfied when m greater than 2 or n does not equal k. Similarly, in Eulerian cycle in GF, m can be represented by a vertically periodic 2k times 2n m plus 1 k plus m matrix, and if the first m columns equal the last m columns, the cycle can be represented by a doubly periodic matrix, forming a 2k, 2n, m plus 1 k, n, m plus 1 dBA. The authors are not interested in codes with one code word, as these are just de Bruijn arrays, but these codes can be used in recursive constructions. In 2k, 2t, n, m, dBAC can be generated from GF, m, where the columns of the arrays are taken from a PF, n, k, and such a code can be viewed as a factor in GF, m. Any cycle of length 2t in GF, m can be represented by a 2k times 2t plus m1 matrix, but to be a code word in a dBAC, the 2k times m1 matrices obtained from the first m1 columns and the last m1 columns of each matrix must be equal. The authors note that there are 2k, 2t, n, m, dBACs whose columns do not form a perfect factor in Gn. The graph GF, M can be viewed as a two-dimensional generalization of the de Bruijn graph, and a factor in the graph is a state diagram for a two-dimensional generalization of non-singular feedback shift registers. The generalization for two-dimensional feedback shift registers using a perfect factor Pf, n, k, is straightforward, where the perfect factor f has two nk cycles of length 2k. Two-dimensional feedback shift registers are essential components in de Bruijn arrays codes. A novel method for developing a theory for these registers is introduced, defining non-singular two-dimensional feedback shift registers as those whose state diagrams contain only cycles. This allows for the generalization of the Majorsplit method from unidimensional to two-dimensional feedback shift registers, enabling the combination of two cycles into one when applying this method on companion vertices. The paper presents 5 direct constructions for de Bruijn arrays codes. The first construction focuses on creating 2k, 2t, n, 1 dBACs for all possible parameters. This is based on the observation that each n-tuple is contained in exactly one column of the arrays, implying a perfect factor in Gn with 2n-k cycles of length 2k. A derived theorem states that in 2k, 2t, n, 1 dBAC exists if and only if there exists a perfect factor, n, k. A corollary specifies the conditions under which such an array can exist, namely when k is less than or equal to n less than 2k, i.e., n less than 2k is less than or equal to 2n. These constructions are crucial for the recursive constructions presented in subsequent sections and for applying the Majorsplit method on some dBACs, allowing for the analysis of the parameters of the 2k, 2t, n, m dBACs obtained. The significance of these constructions lies in their ability to facilitate the development of de Bruijn arrays codes with specific parameters, enabling further research and applications in coding theory. The construction of 2k, 2t, n, 2 dBACs, particularly when t greater than 1, is a significant area of research. If there exists a Pf, n, k, with 1 is less than or equal to nk, then a 2k, 2t, n, 2 dBAC can be constructed. For instance, when k equals n1 and t equals n, Case 1, 2 codewords are generated. Each pair of sequences from the PF, N, K, appears exactly once in one of the 2 codewords, making the constructed code a 2K, 2T, N, 2, DBAC. In another case, where K equals N1 and T equals N1, case 2, 4 codewords are constructed. The first 2 codewords are similar to those in case 1, but with smaller shifts and fewer columns due to the smaller value of T. The remaining 2 codewords are defined differently, ensuring that each required pair appears exactly once in one of the 4 codewords, thus creating a 2K, 2T, N, 2, DBAC. In both cases, the sum of all the shifts is 0 modulo 2K, which is crucial for the construction of the DBACs. The pairs of sequences in the PF, N, K, must be arranged as columns in the 2K times 2T arrays such that each N times 2 matrix is contained as an N times 2 window in exactly one of these arrays. This ensures that the constructed code meets the requirements for a 2K, 2T, N, 2, DBAC. This section presents novel ideas and significant findings in the field of DBACs, providing a direct construction method for 2K, 2T, N, 2, DBACs when K equals N1. The approach involves leveraging the properties of PF, N, K, to guarantee that each ordered pair of sequences appears exactly once in one of the codewords, resulting in the desired DBACs. This section of the research paper delves into the construction of a 2K, 2T, N, 2, DBAC, a combinatorial structure crucial in coding theory and cryptography. The paper explores 3 distinct cases for the parameters k, n, and t, where k less than n less than 2k and 2 is less than or equal to t is less than or equal to 2nk1. In case 1, the authors meticulously analyze the pairs of sequences that can be formed within the first 4 codewords. They illustrate how these pairs are distributed across the codewords, ensuring that no 2 sequences in a pair appear together in any codeword. This leads to the conclusion that C is a 2K, 2T, N, 2, DBAC. Case 2 is a generalization of case 1, with the additional constraint that T equals K. The analysis follows a similar pattern to case 1, resulting in the same conclusion about C being a 2K, 2T, N, 2, DBAC. Case 3 introduces an additional set of codewords and analyzes their properties. It also discusses the construction of remaining codewords and their relationships with previous ones. The authors conclude that C is a 2K, 2T, N, 2, DBAC for this case as well. The paper then generalizes the construction to any set of parameters for a 2K, 2T, N, 2, DBAC, where k less than n less than 2k and 2 is less than or equal to t is less than or equal to 2nk1. This is achieved by applying the same methodology to each pair of sequences in the PF, N, K, and constructing the necessary codewords. Finally, the authors present corollary 3, which states that if k less than n less than 2k and 2 is less than or equal to t is less than or equal to 2nk1, there exists a 2k, 2t, n, 2, DBAC. However, the technique used in the paper does not cover the case where k equals n, as the perfect factor contains only a span n de Bruijn sequence. Binary block array codes, denoted as BBACs, are a novel type of binary block codes characterized by their parameters 2k, 2t plus 1, n, 2t. This research presents a method for constructing BBACs using perfect factors, or sequences of a certain length and linear complexity, derived from a given de Bruijn array code, DBAC. The authors prove the existence of perfect factors without self-dual sequences for specific values of n and k, ensuring the feasibility of this construction approach. The process begins with the selection of a DBACC with parameters 2k, 2t, n, m, and a perfect factor f with specific properties. The sequences of f are used as indicators associated with the columns of the codewords of C. By combining these components, the authors demonstrate how to construct the BBACC, ensuring that the resulting code has no smaller horizontal periodicity and thus achieving the desired properties. Notably, this research also introduces a recursive construction technique for de Bruijn arrays codes. This approach involves using a given DBAC and a perfect factor to create a new DBAC with specified parameters. This method enables the creation of more complex and diverse BBACs based on existing ones, expanding the range of possible constructions and applications of these codes. Overall, this novel method provides a systematic approach to generating BBACs with specific properties, enhancing the versatility of these codes in various contexts. The authors introduce Theorem 10, which generates a new 2K, 2 meters, n+1, m, DBAC of size 2 meters delta from an existing 2K, 2 meters, n, m, DBAC of size delta. This is achieved by applying the inverse of the decimation operator d-1 to the columns of the original code words, resulting in complementary sequences of the same period 2K. These sequences are then used to construct a new 2K times 2 meters doubly periodic array, part of a new code C. The authors prove that the new code C has 2 meters delta codewords, each with 2K plus m distinct windows of size, n+1 times m, resulting in a total of 2K plus m 2 meters delta windows of size, n+1 times m. To complete the proof, they demonstrate that all the n+1 times m windows in the codewords of C are distinct, assuming for the contrary that there exist two identical windows in two codewords of C, and deriving a contradiction. The implications of Theorem 10 are discussed, noting that it cannot be used to obtain DBACs with new parameters directly. However, by transposing the obtained DBACs and applying the recursion, they can obtain DBACs with new parameters. The weight of the rows in the direct constructions is examined, focusing on two specific constructions obtained from Theorems 8 and 9. It is found that the construction in Theorem 9 yields DBACs with new parameters, as the rows have even weight, and that another iteration of d-1 yields sequences with odd weight. Overall, Theorem 10 provides a recursive construction for DBACs, which can be used to obtain new DBACs with larger parameters. The authors emphasize the significance of this construction in the context of other recursive constructions. Theorem 11 demonstrates that if a 2K, 2 milliliters, n, m, DBAC of size increment exists, with columns being sequences of period 2K and even weight, then a 2K, 2 milliliters, n+1, m, DBAC of size 2 meters increment can be constructed. This is achieved by applying a similar technique to that used in Theorem 10, but with span m sequences of a perfect fanout, m, ml, instead of a single de Bruijn sequence. Theorem 12 presents a more general construction, where if a 2K, 2t, n, m, DBAC of size increment exists, with columns being sequences of period 2K and even weight, then a 2K, 2 meters plus t, n+1, m, DBAC of size increment can be constructed. This is achieved by defining a new array B from a codeword A in the original DBAC, using a span m de Bruijn sequence S. The columns of B are constructed by applying the operator D1 to the columns of A, resulting in a doubly periodic array with 2K plus m plus t windows of size, n+1 times m. The theorem is proved by showing that each n+1 times m binary array is contained at most once as an n+1 times m window in some B. The recursive construction in Theorem 12 enables the creation of DBCAs with new parameters, where the horizontal length of the array increases without enlarging the horizontal length of the windows. Additionally, this construction can be applied to transposed arrays, similar to the constructions in the previous two theorems. Here are three theorems that focus on the construction of doubly periodic arrays of binary codes, or DBACs, with new parameters. Theorem 13 states that if a 2K, 2T, n, m, DBAC of size increment exists, with columns being sequences of period 2K and even weight, then a 2K, 2 meters plus T1, n+1, m, DBAC of size 2 increment can be constructed. This is achieved by using a span m half de Bruijn sequence and its complement to form codewords. Theorem 14 establishes that if a 2K, 2T, n, m, DBAC of size increment exists, with columns being sequences of odd weight, then a 2K plus 1, 2T, n plus 1, m, dBAC of size 2m1 increment can be constructed. The proof involves applying the inverse of the D transformation to columns of a code word to obtain self-dual sequences, which are then used to construct a new array. This theorem also provides an analysis of the new dBAC's properties, including its size and number of windows. Theorem 15 states that if a 2k, 2t, n, m, dBAC of size increment exists, with columns being sequences of odd weight, then a 2k plus 1, 2 meters plus t1, n plus 1, m, dBAC of size increment can be constructed. The proof involves defining a new code word by taking 2m1 copies of a code word in the original dBAC. The implications of these theorems are significant, as they provide a recursive construction method for obtaining dBACs with new parameters by applying these theorems to previously constructed dBACs. A 2k times 2 meters plus t minus 1 doubly periodic array, codeword A, is used to construct self-dual sequences of length 2k plus 1 by applying the operator d minus 1 to its columns. These sequences are then used to build a new array B, comprising 2t copies of a span m half de Bruijn sequence and its shortened version, with the first m bits being zeros. Array B is a 2k plus 1 times 2 meters plus t minus 1 doubly periodic array with 2k plus m plus t windows of size, n plus 1, times m. The ith column of B, bi, is defined as bi equals d minus 1 bi, where I is the ith column of A, and 1 is less than or equal to I is less than or equal to 2 meters plus t minus 1. The codeword B is used to construct a new code C, which is A, 2k plus 1, 2m plus t minus 1, n plus 1, m, dBAC of size increment. This is proven by showing that all n plus 1 times m windows in all codewords of C are distinct. The construction of Theorem 15 yields dBACs with new parameters, similar to those in Theorems 12 and 13. Note that columns of length 2k with different periods can also be used, but were not included to avoid added complexity. The paper also presents a construction for 2k, 2t, n, m, dBACs from 2k, 2t, n, m, dBACs, where t is greater than or equal to t, by joining cycles in the factor graph. This construction involves ordering codewords in pairs, with each pair having a pair of companion states, and joining them using the merge-or-split method. This process can be continued, generating a 2k, 2t plus 1, n, m, dBAC of size increment, 2. Two examples are provided to demonstrate the idea, starting with the cycles of a 2k, 2t plus 1, n, 2t, dBAC obtained from the construction of Theorem 9. The goal is to order the codewords in a list such that each two consecutive codewords have a pair of companion vertices and can be merged together using the merge-or-split method. A new family of self-dual codes is constructed, focusing on the case where n equals 2t plus 1 and k equals t. A mapping phi from F to F2 is defined, which maps each cycle xi in F to either 0 or 1 based on its index. This mapping induces a mapping from the codewords of C to the set of self-dual sequences of length 2t plus 1. The authors determine the number of codewords of C that are mapped into a given self-dual sequence S of length 2t plus 1, showing that this number is 2, nk1, 2t 2k, 2t1. This is because there are 2, nk1, 2t distinct choices for the first 2t coordinates with zeros and 2k, 2t1, distinct choices for the remaining coordinates with zeros. To simplify the understanding of the ordering, the authors consider a self-dual sequence S and its 2t coordinates which are zeros. They define an ordered set Q1 consisting of tuples representing the shifts of the cycles, xi1, xi2, xi2t, in a codeword C. The 2k, 2t1, elements of Q1 are ordered in a cyclic gray code, ensuring that each two elements differ in exactly one position. The authors prove that if two elements of Q1 differ in exactly one coordinate, their associated codewords can be combined into one codeword using the merge-or-split method, as they have a pair of companion vertices. This construction is crucial for the overall development of the new family of self-dual codes. In the construction of 2k, 2t plus 1, n, 2t, DBAC codes. The authors prove that two codewords in Q1 differ in exactly one coordinate, implying that the associated codewords of C1 and C2 differ in exactly two coordinates separated by two T1 coordinates. Since C1 and C2 are identical, these two 2k times 2t matrices associated with these two T1 coordinates and the coordinate that follows them differ only in the last column, making them companion vertices. The cyclic gray code of the elements of the set Q1 and lemma 14 imply that a cyclic gray code can be formed from the codewords of each equivalence class. To order the codewords from different equivalence classes associated with the same self-dual sequence S, the authors define another gray code on the set of elements Q2. Specifically, the element I1, I2, I3, I2t in Q2 is associated with the equivalence class She1, She2, Xi2t. The authors demonstrate that a pair of companion vertices in two distinct equivalence classes associated with the same self-dual sequence S, which differ in exactly one coordinate of Q2, can be found. According to lemma 15, if I1, I2, I3, I2t in Q2 and I1, I2, I3, I2t in Q1 differ in exactly one coordinate, then their associated codewords in the associated equivalence classes can be combined into one codeword by the mergeorsplit method, yielding a pair of companion vertices. Considering two self-dual sequences of length 2t plus 1, S1 and S2, which differ in exactly two coordinates I and I plus 2t, lemma 16 states that any two self-dual sequences of length 2t plus 1, which differ in exactly two coordinates, have in their associated codewords a pair of codewords whose vertices have a pair of companion vertices. Ultimately, the authors combine all the cyclic lists into one cyclic list containing all the codewords, where each two consecutive codewords have a pair of companion vertices. This is formalized in Theorem 16, which asserts that all the codewords of a 2k, 2t plus 1, n, 2t, DBAC code obtained in the construction of Theorem 9 can be ordered in a cyclic list in which each two consecutive codewords have a pair of companion vertices. The construction of a 2k, 2t plus 1, n, 2t, DBAC code is facilitated by the concept of companion vertices and equivalence classes. This process begins with a list of codewords from a self-dual sequence, which are then merged into one cyclic list. Each two consecutive codewords in this list have a pair of companion vertices, ensuring that the resulting code meets the requirements of a 2k, 2t plus 1, n, 2t, DBAC. To initiate this process, the codewords are partitioned into equivalence classes based on their representation as words of length 2t. Each codeword C is represented as She1, EJ2 She2, EJ2 T11 2t, where She and EJ are elements of a finite field F. This representation is chosen to be the one among the two T cyclic shifts of C with the smallest lexicographic value for She1, She2, She2t. An equivalence relation is defined on all the codewords of C, where two codewords are considered equivalent if they differ only in one coordinate. This means that each equivalence class consists of codewords that can be transformed into each other by applying a sequence of transpositions of coordinates. To merge the lists of two different equivalence classes for the same self-dual sequence, the lists are combined in a specific order. The first element of the first list is followed by the last element of the second list, then the second element of the first list is followed by the second last element of the second list, and so on. This process continues until all elements from both lists are combined, resulting in a new cyclic list where each two consecutive codewords have a pair of companion vertices. The same merging process is applied to combine the codewords of distinct self-dual sequences. For instance, let S1 and S2 be the first two self-dual sequences in the list. Since S1 and S2 differ in exactly two coordinates, we take two equivalence classes that differ only in these coordinates and merge the two lists using the same idea as before. The outcome is a cyclic list with all the codewords of C, where each two consecutive codewords have a pair of companion vertices. A corollary presented states that if k and n are integers such that k less than n less than 2k, then there exists a 2k, 2t plus 1, s, n 2t dbac of size 2n 2t minus k minus t minus 1 minus s, where 0 is less than or equal to s is less than or equal to n 2t minus k minus t minus 1. An example of this list of codewords is too large and hence omitted, leaving it for the interested reader to explore further. A second example of the method is to start with the codewords of a 2k, 2t, n, 2t-1 dbac code obtained from the construction of Theorem 8 with f as the pf, n, k. This code has 2 nanometers minus k minus t codewords, where m equals 2t-1 and t is greater than or equal to k. The codewords are partitioned into equivalence classes as described above, and then the lists of different equivalence classes are merged to form a cyclic list where each 2 consecutive codewords have a pair of companion vertices. In constructing codewords within an equivalence class, each shay, except the last, can be chosen in 2 n-k distinct ways, resulting in a total of 2 n-k, 2t-1 distinct choices. The last shay is determined by the equation P2tr equals 1ir is defined as 1 mod 2n-k. Since each of the 2t cycles from f in the equivalence class, she1, she2, she2t, can be chosen as the first one, the number of equivalence classes in this equivalence relation is 2 n-k, 2t-1, minus t, 2t equals 2 n-k, 2t-1, minus t. Merging codewords within each equivalence class can be done exactly as in the first example. The first sequence is taken in its 0 shift, and the next 2t-2 sequences can be taken each one in any of its 2k distinct cyclic shifts. The shift of the last sequence is determined such that the sum of all shifts is congruent to 0 modulo 2k. 2 codewords of an equivalence class that differ in exactly 2 consecutive shifts have a pair of companion states, since the number of columns of a state is 2t-1, and these 2 codewords can be horizontally shifted to share the first 2t-2 columns and their shifts. The set Q3 is defined, whose elements define the shifts of the sequences from FQ3 is defined as 0, J2, J3, J2t, 0 is less than or equal to JL is less than or equal to 2k-1, 2 is less than or equal to L is less than or equal to 2t, n array product L equals 2t JL is defined as 0, mod 2k. The element, 0, J2, J3, J2t, element of Q3 for the equivalence class, she1, she2, she2t, is associated with the codeword, she1, ej2 she2, ej2 t11 2t. The authors discuss the need to order the elements of Q3 in a cyclic list such that each 2 elements in the list differ in exactly 2 consecutive elements. Such a list implies that each number of consecutive elements in the list can be merged together via the merge-or-split method. A longer cyclic list that includes all the codewords of C can be achieved by ordering the equivalence classes in another cyclic list, where each 2 consecutive equivalence classes in the list differ in exactly 2 consecutive elements. However, the authors note that they do not have a general construction for such a list and leave it as a problem for future research. When the number of sequences in F is 2, i.e., n-k equals 1, it is relatively easy to generate such a list. The list consists of all the cyclic sequences of length 2t and odd weight. An example of such a list is provided, where the sequences are ordered in a way that each 2 consecutive elements differ in exactly 2 coordinates. Another example of a list with all the elements of Q3 is also provided, where the elements are presented as column vectors, demonstrating the construction of codewords in an equivalence class. De Bruijn array codes, a generalization of traditional de Bruijn arrays, are introduced in this paper. A novel construction method is presented, combining direct constructions, merge-or-split techniques, and recursive constructions. The necessary conditions for creating these codes are outlined in Lemma 1, with the authors conjecturing that these conditions are also sufficient. However, proving this requires further constructions, left for future research. Examples of specific de Bruijn array codes are provided, including A, 4, 22 plus I, 3, 3, dbac for each I. 0 is less than or equal to I is less than or equal to 5, obtained through the merge-or-split method. Additionally, pseudo-random array codes are introduced, a generalization of pseudorandom arrays, with an algebraic flavor contrasting the combinatorial flavor of most de Bruijn array code constructions. A follow-up paper is planned to comprehensively explore pseudorandom arrays. The paper concludes by posing two open questions related to the ordering of codewords in a given code C, specifically involving the set Q4. Defined as I1, I2, I3, I2t, 0 is less than or equal to il is less than or equal to 2n-k-1. 1 is less than or equal to L is less than or equal to 2t. Sigma 2tl equals 1 il is defined as 1, mod 2n-k. This set is crucial for understanding the structure and properties of de Bruijn array codes and their applications in computer science and information theory. De Bruijn sequences and arrays are fundamental concepts in various fields, including error correction, cryptography, and pseudorandom number generation. They have been applied to multidimensional cluster errors and interleaving schemes with repetitions, providing constructions and bounds for these concepts. This paper provides a comprehensive review of different approaches to constructing de Bruijn arrays, such as the use of homomorphisms, pseudorandom arrays, and perfect maps. The complexities of de Bruijn sequences and the existence of de Bruijn tori with 2x2 windows are also explored. Moreover, the application of de Bruijn sequences in structured light 3D surface imaging is discussed, highlighting the importance of these sequences in enhancing the accuracy of this technology. De Bruijn arrays play a significant role in designing universal test sequences and are relevant in the context of feedback shift registers. The paper concludes by emphasizing the significance of de Bruijn sequences and arrays in various areas of computer science and information theory, underscoring the need for continued research in this field to uncover new constructions and applications. The authors present a comprehensive list of 17 heterogeneous benchmark datasets, carefully curated to encompass a diverse range of applications, including computer vision, natural language processing, and recommender systems. These datasets are deliberately chosen to exhibit varying degrees of complexity, noise, and dimensionality, thereby facilitating a thorough evaluation of the proposed methodology. The datasets are categorized into three distinct groups: synthetic, semi-synthetic, and real-world datasets. The synthetic datasets, totaling 5, are generated using stochastic processes and are designed to model specific types of data distributions. The semi-synthetic datasets, consisting of 7, are derived from real-world data but are augmented with artificially introduced noise and perturbations. The real-world datasets, 9 in total, are sourced from various application domains and are characterized by their inherent complexity and variability. Each dataset is accompanied by a detailed description, including its origin, size, and inherent characteristics. This information enables a comprehensive understanding of the dataset's properties and facilitates the interpretation of the experimental results. The authors also provide a concise overview of the preprocessing techniques employed to prepare the datasets for experimentation, including data normalization, feature scaling, and handling of missing values. The presented benchmark suite is designed to serve as a standardized platform for evaluating the performance of various machine learning algorithms and models, particularly those tailored for heterogeneous data. By providing a diverse and comprehensive set of datasets, the authors aim to facilitate a fair and unbiased comparison of different methodologies, ultimately contributing to the advancement of the field.